to worry about. All right. Okay. So average value. I accidentally gave you one a little bit ago about average value, which we kind of figured out, even though we didn't know how to do average value yet. But we're going to sort of solidify what to do here for your average value a little today. So this graph above shows the velocity of a car as it travels down a track where V of t is measured in feet per second and t is measured in seconds. Find the average velocity of the car for t equals 0 to t equals 60. So looking at this graph right here, it tells us t is measured in seconds, which I already labeled. I think I didn't mean to label that yet, but it's labeled there for us. We also know V of t is measured in feet per second, so that y-axis is feet per second. And we're supposed to find the average velocity of the car. So average velocity is, or let's just say average speed is pretty easy to find, right? Like if I just have you, like if you drive from, I've said this a bunch of times, if you drive from here to Winston and it's 50 miles and it takes you 1 hour, how do you figure out your average velocity? In miles per hour, not feet per second. That'd be harder. It's just distance divided by your time, right? So if you want miles per hour, it'd be 50 miles in 1 hour. 50 divided by 1 would give you 50. Your average speed was 50 miles per hour, right? Now, that is knowing distance. Do we have distance on this graph right here? We do not. So this particular one is a little bit easier to sort of see because we have a straight line right here for this. So what is my velocity here whenever time is 0? 70. And what is my velocity here whenever time is 60? 130. So if my velocity is 70 at the beginning and 130 at the end, what do you think average velocity was? That is lower than our lowest velocity. So no, that would not be a good guess. All right, 70 is the lowest the velocity ever is. And the velocity consistently increases until it gets up to 130. All right? So 70 would be your lowest velocity. It's not going to be your average. Your average is going to be higher than 70. And it's going to be lower than 130. So what do you think? 100, right? 100 would be halfway between 70 and 130. Right? So now that will work for this particular graph because it's a straight line, right? You are increasing at the same amount. But let's think about this and what we would need to do this even if it was not a straight line. So my average velocity, technically this is average speed, but since my velocity is positive the whole time, this will work as well, should be my distance divided by my time. Now, I don't have a graph for distance. I have a graph for velocity. How do I find distance from a graph of velocity? I would integrate. And integrate is the area underneath the curve, right? So when I find the area of this shape right here, right, I'm integrating. So I would be taking, I'm going to use a trapezoid for that. You could use like a triangle and a rectangle if you want. But this side right here is 70. This side right here is 130. This side right here is 60. So you would do 1/2. We'll use D for distance. 1/2. What's the area of your trapezoid? 1/2 what? Base 1 plus base 2 times what? The height. What is the height on this one? 60. So you've got 70 plus 130 times 60. So it's half of 200 times 60. So that is going to be 6,000 feet. Okay. Units, whenever we integrate, whenever you're thinking about units, because they're really important on a problem like this, if we are integrating, we're taking our units for our y-axis and multiplying it by the units for the x-axis, which is seconds. Seconds cancel, we just get feet. If we are taking the derivative, we do change in y over change in x. Derivative would give us feet per second, so that would give us acceleration, which is not what we want here. So this is just my distance. My distance is 6,000 feet. What was my time? 60 seconds. And so that is going to give me 100 feet per second. Now, I want to kind of show you a little bit of what exactly is happening here. This car was only going 100 feet per second one time, right? One point. At this point right here. But because this is a nice straight line, it makes it a little easier to picture here. If I take this little piece right here and I flip it around and I add it over here, then I would just have a rectangle, right? I could turn this into just a rectangle if I take that green piece away, like cut it out and move it over here because those are the same size. So the car accelerating in this manner would be the same as if it was just going 100 feet per second the entire time, right? If it was going 100 feet per second for 50 seconds, or for 60 seconds, we'd just do 100 times 60, it'd give us 6,000 feet, right? So that's sort of the idea of what is happening here. You're trying to find that number that would just like turn this into a rectangle that would have the same area as the area under the curve for that. Okay, questions? Okay, now I do want to write sort of what we did right there. What we did is we integrated v of t from 0 to 60, and then we divided it by our difference in our time, which was 60 minus 0 here. Right, that we integrated velocity, and then we divided it by our time. If you also sort of think about what's happening with units here, when we integrate velocity, our units are feet, but then by dividing it by time, we turn it back to feet per second, right? So if we just needed to know the distance the car traveled, we just integrate and we get 6,000 feet. But if we want to know average velocity, we can take that distance, we can divide it by the amount of time, and it turns it back to feet per second, giving us an average velocity for that. This is another thing we talked about once with this was, I think it was Troy's ability to get here from Yadkinville in 10 minutes, which is questionable there in safety. You know, the average speed that you would have to get would be way too fast, and you should not do that. Yeah, it was like 100. I dread Hunter getting his license. All right, now let's look at just more of like a naked problem here. Okay, this problem doesn't have context to it. So we've got a graph of f of x. It's shown here. We're supposed to find the average value of f on this interval, right? Now, this one is a more complicated looking graph, right? In this particular graph, we've got, it's going to be a lot harder to like take a piece and sort of fill in to make a rectangle here, because especially when you get over here to this semicircle, right? It's going to be, how much of this do we need to take away to fill in over here? This, if you're sort of thinking of it like we could take that piece away and put it over here, that makes it more rectangle-y, but like I got 3 more blocks over here. That looks like just like more than 3 blocks, so then I got to take like a slice and spread it out. Like, it would be way more difficult to rearrange this to be a rectangle. But we're sort of thinking about trying to make a rectangle out of this. So all we have to go on is f of x, and f of x is given to us here. So if I integrate f of x from -4 to 4, right, so we're looking from here to here, I want to integrate from -4 to 4 f of x dx, and that is going to give us, in this particular case when we're doing a graph, the integral is the area under the curve. If we had equations, we'd need to like actually integrate the equation, but when we're looking at a graph, the integral gives us the area under the curve. So if we split this up here, we have a rectangle right there that has an area of 9. Then we've got here a trapezoid that would be 1/2, a height of 2, and then 1 plus 3 right there. This 2 right there being our height, the 1 and the 3 being our bases for that. Then I'd probably do this rectangle right here that has an area of 3, and then you've got half of the circle, so that's going to be 1/2 pi r squared. The radius of that circle is just 1, so 1 squared goes there. Okay, so I'm going to put that 9 and that 3 together to give me 12. This is going to be 1/2 times 2 is just 1, so it's going to give us 4 right there. And then we're going to have pi over 2 whenever we do our 1/2 pi times 1 squared. And so without a calculator, the best you're going to do on this is just 16 plus pi over 2. Now, that does not give us the average value of the function. That gives us the area under the curve. So the way we turn this, and if you think about this, when you integrate f, you're going to like capital F, right? You're getting a different function right there. To get back to little f, we need to divide, right? If we think about our units, if this is feet per second, when we integrate, we just have feet. It's like our distance, even though this particular one's not in the context of distance. So if we want to get back to f, we've got to divide by whatever's on that x-axis. So what we need to do is we need to take that value that we just found, 16 plus pi over 2, and we need to divide it by the length of the interval, right? What's our length of our interval here? It is 8 in this case. And I'm going to do this. I'm going to do 4 minus -4, because we're going to see something like that in a second. You wouldn't necessarily have to show that. So that would be divided by 8. They might just leave it like that. They might love connection this. So you would get 2 plus, that's going to be pi over 16, because you'll be doing pi over 2 divided by 8, which is like 8 over 1. So that is pi over 2 times 1 over 8, which is going to give you pi over 16. And that would be your average value of f. And if we take the calculator real quick and do 2 plus pi over 16, just to kind of, if we get a decimal for that, it's 2.196 is the decimal value for that. So what that's telling us is if we came over here and we went at 2.196, so about right there. If we made a rectangle right here that was like that, let me highlight here. If we made this rectangle right here, that would have the same area as the area under the curve of the function, right? So you see like this little sliver of extra right here, if we were to turn it over and fill in this area, it doesn't even look quite right. I probably need to move my line down just a little bit, but your extra right here could be filled in over here to make a rectangle. For that. Okay, questions? Okay, let's talk about just the general formula if something asks you for average value. So if you see average value of a function f on the closed interval from A to B, this could be what is the average velocity, what is the average acceleration. It could be what is the average number of fish in the pond. It could be just what is the average value of f of x or f prime of x. Sometimes it'll actually say average value. Over it'll say average of whatever they're wanting, right? If they're given this on a closed interval, then you want to do 1 over b minus a. B minus a is just length of your interval, right, times the integral from a to b of that function. Now, this is important right here. Notice you're finding average value of f. You're using f right here, okay, for that. On this, and this part right here is your, let's write that down. This part right here is your length of the interval. There. Okay, and this would be the height of your mean value rectangle. So if if we made our shape into a rectangle, it's the height of that rectangle for that. So sometimes you just get like a naked problem like this. Find the average value of f of x equals 3x squared minus 5x plus 2 on the interval from 1 to 3. Okay, so using that formula that we just had, it's going to be 1 over the length of the interval, so you're doing 3 minus 1 there, times the integral from 1 to 3 of 3x squared minus 5x plus 2 dx. This is essentially what we were just doing, where we like integrated to find distance, and then we divided it by the time there. This 1 over 3 minus 1, that's your dividing. It's sort of factored in there for you. So you're going to have 1/2. Put your bracket right here, or parentheses, but I like a bracket so it doesn't get mixed up. We want to integrate here, so we're going to do x to the third. 3 divided by 3 is just 1, so we don't have anything out front there. Then we're going to have x squared. We'll have to have a 5/2 here, and then we'll get a plus 2x. We do not need a plus c because this is a definite interval. We're plugging numbers into this, so we're going from 1 to 3. Okay. Once I integrate, what do I have to do now? I'm going to subtract. I'm going to plug in the 3, plug in the 1, subtract those values, right? So keep your 1/2 out front till the end. You're going to have 3 cubed minus 5 halves times 3 squared plus 2 times 3 minus 1 cubed minus 5 halves times 1 squared plus 2 times 1. And so that's going to give us 27 minus, it's going to be 9 times 5, so 45 over 2 plus 6 minus 1 minus 5 halves And if this were free response, we could have stopped already. We could stop right here for FRQ. You wouldn't have to simplify that, but it might show up on multiple choice as well, in which case you will have to simplify. So let's see, we got 27 plus 6 is going to give us 33 minus 45 over 2. And let's just go ahead and distribute. I'm going to play it safe here. 3 minus 5 halves. Alright, and then that is going to give us 33 minus 45 over 2 minus 3 plus 5 over 2. And that's going to be half of 30. And then we got negative 45 over 2 plus 5 over 2, which is going to give us negative 40 divided by 2, which is negative 20. So we got minus 20. And so we got half of 10, which finally does just give us 5 as our answer. The majority of that work right there is arithmetic. For that, if it is for response, you would stop here. You don't need to work that out. Everybody okay here? All right. I've got one more for us. The velocity of a particle traveling along the x-axis is given by v of t equals x times the square root of x squared plus 1. What is the average velocity of the particle for negative 3 less than or equal to t less than or equal to 3? Okay, so we're given our velocity. If we want average velocity, then we need to do 1 over length of the interval times the integral of that function, right? So our length of our integral here is 6. From negative 3 to 3 is 6. We need to integrate from negative 3 to 3. And I've got x square root of x squared plus 1 dx. How am I going to integrate this one? What? We got to do u du. So u, in this case, what would it be, Liam? Good. And then what is du? Almost. What is the derivative of x squared plus 1? 2x dx. So we've got our x here and our dx, which we need, but we're missing the 2. So we're going to put a 2 right here, which means we must put a 1/2 out front. Now, if you remember on these types of problems, I've got options on whether or not I want to change my interval right here. I do want to change my interval, okay? Especially on this one, it makes it a lot easier if you do. So what this is going to look like, this stuff right here is my du. The stuff underneath, that's my u. So I'm going to have 1 over 12. I'm going to go ahead and put those two fractions together. And then I will be integrating the square root of u du. And then what I want to do for my limits is I want to plug them into u, and then I don't have to go back to the x's. And we're going to see something helpful happen here. Because if I take negative 3 and plug it right here for the x, I'm going to get negative 3 squared plus 1, which is going to be 9 plus 1, which will give us 10. Okay. Then if I do the same thing with my 3 squared plus 1, I'm going to get 9 plus 1, which also gives me 10. What's the answer to this problem? It's 0. for this because anytime you integrate from a number to itself, the width of your interval is 0. So it doesn't matter what the function looks like, your width is 0, and you're going to get 0 for that. Let's look at this graph on Desmos just to see why in the world this is happening here. I think that's helpful for us to see. Our equation is x was x square root of x squared. Is it a plus 1 or minus 1? Plus 1. Alright, here's our graph. I'm going to put in a line at x equals -3 and x equals +3. Why did this happen? Why did we get 0? They cancel out. You got this area underneath the curve here, right? That's going to be negative. And this area over here underneath this curve that's positive, and they're the same shape, right? Because of the symmetry of this graph. So whenever you find that integral, you just get 0. So the velocity, average velocity is 0. Now, velocity was only 0 one split moment right there. Not even a moment, like a, you know, there's not even a unit of time to tell you. It's a point in time that came and went. You can't say even like a millisecond because that has width to it. Like at a tiny point right there that has no amount of length, you are at 0. But the rest of the time, the particle is moving, right? But it was going in a negative direction here. Then it turned around and it went in a positive direction. And that canceled each out with that negative and that positive velocity. Okay? But I have a different question for you. This question is, what is the average speed of the particle? It seems almost like the same question. In like real life, we use those two kind of interchangeably, right? You know, if I ask you your average speed when you're driving somewhere, if I asked you your average velocity when you're driving somewhere, you're probably not considering your direction, right? Although technically you should. But speed has no direction. So what does that mean about this over here? It's positive. In fact, what it really is going to look like is if we put absolute value bars around this, it would look like this. That's our graph of speed, because speed is just the absolute value of your velocity. Now, do we really know how to like take an integral of an absolute value? We do not. Now, if this were calculator active, we could do that, and I'll show you that in just a second. But it's I think probably not going to be calculator active. So instead, what we're going to have to do is we are going to have to think about where this graph is negative and where this graph is positive. This graph is going to be negative anytime x is negative, and it's going to be positive anytime x is positive, right? So what we can do for this is we can break our integral into two sections, right? So we can do the integral from -3 to 0 of x square root of x squared plus 1 dx. And then we can do the integral from 0 to 3 of x square root of x squared plus 1 dx. But I'm going to put a negative out here in front of this one because I know since the velocity is negative on that interval that I need to put that extra negative to turn it back to a positive for that. So much like the last problem, we're still going to use a u as x squared plus 1 for both of these right here. And then and also this whole thing needs a 1/6 out front. You don't want to do like a 1/3 and a 1/3. It might work out in this case, I'm not sure, but there are times when it will not. I'm not 100%. You want to do, this is our like area under the curve. And we'll take that whole thing and divide it by 6. We don't want to do those separately by 3 and 3. Sometimes they'll give you a different answer. So du, green here, du will be 2x dx. Just like the last one, we had 2 here and a 1/2 out front. 2 here, 1/2 out front. So we're going to have negative 1/2 integral of u, square root of u, du, plus positive 1/2 integral square root of u, du. And I purposefully held off on those limits because I want to switch those to x's. Let me see where you're at so far, if you're okay. Questions in this? This part right here is our u, also u over here, and then this part right there is our du. This part right here is our du. We're okay so far? Alright, I'm going to switch my limits. So, over here, you got to do negative 3 squared plus 1, which we already did. That gave us 10. So, we're going to get 10 right here. When we plug in 0, 0 squared plus 1 is going to give us 1. And then over here, we got to do the same thing. 0 squared plus 1 is going to give us 1 for our lower limit. And 3 squared plus 1 is going to give us 10 for our upper limit. Now, what's wrong about this first integral that we've got? It's backwards, right? So if I flip it around, what have I got to do with my limits? Or what have I got to do? If I make this 1 to 10 instead of 10 to 1, it's going to make this negative, but since it's already negative, it actually is going to make it positive in this case. Square root of u plus 1/2 integral 1 to 10 square root of u. Now, does anybody else see something I can do here to make this a little bit easier of a problem? I could take out the 1/2, or this and this are the same integral, right? So if I've got half of something plus half of that same thing, what's it give me? The whole thing, right? So I can just make this 1/6 times the integral from 1 to 10 of, I'm going to write that as u to the 1/2 du because I'm getting ready to, like that. So if I got half of the integral plus half of that same integral, it's just 1 of the whole integral. Does that make sense? That doesn't always happen, but it did on this one. So now I'm down to pretty basic integration here. I need to integrate u to the 1/2. I'm going to increase my exponent by 1, which will be 3/2. I need to divide out front, so there's a 1 there, by 3/2. And this will be from 1 to 10. And so 1 divided by 3/2 is dividing fractions easy as pie. Flip the second and multiply. So I got 2/3 u to the 1/2. It might be helpful on this to make that the square root of u cubed. And so I will have 1/6, 2/3 square root of 10 cubed minus 2/3 square root of 1 cubed. And the answer on this is not all that pretty because you can't take the square root of 10 cubed. You could make it 10 root 10 if you want, or just make it root 1,000. I think I'll just leave it root 1,000 minus 2/3. Here, you could distribute that 1/6 if you want. you'll get 2 over 18 root 1,000 minus 2 over 18, but those will reduce. So you get 1/9 root 1,000 minus 1/9. They could write that a lot of different ways. It could be like root 1,000 minus 1 over 9, since they're both over 9 there. They might write that root 1,000, 10 root 10 minus 1 over 9. If it is FRQ, stop here. There's no need to simplify it unless you need it for something else. If it's multiple choice, or like whenever you're doing problems from the book, just try to get it to match. So, while our average velocity was 0, our average speed did actually have a value, right? We could actually type that in and get a number for that. In fact, let's see what it is. Square root of 1,000 minus 1 divided by 9. It is 3.40253. Okay. Just calculate for that. Okay, questions? The big thing that I want to stress to you, the thing I see students making a mistake with the most, is that when you're doing average value, it's 1 over length of the interval times the integral of the function you're finding the average value of. A lot of students want to use like v prime or something, or they don't use the right function for that. You need to make sure you're integrating whatever you are finding the average value of for that. All right, so